What does it mean to be truly alone in the universe? Is it the state of a single world teeming with life adrift in an ocean of sterile planets and silent stars? Or is it something more profound, a solitude measured not in distance but in time? Consider a traveler born in the collapsing heart of a long-dead star system, cast out by gravitational chaos into the great empty gulf that separates the islands of light we call galaxies. For an eternity it knew only the crushing silence of the void, a cold so profound it is not merely the absence of heat but a fundamental state of being where atoms themselves slow to a crawl. Its journey was not a streak of light, but a patient, silent coasting through a darkness so complete that our own sun from that distance would be utterly invisible. It passed through ghostly nebulae, vast clouds of hydrogen that are the birthing grounds of future suns, yet it felt no warmth. It drifted by rogue planets, orphaned worlds, banished from their own systems, locked in a permanent, starless night. It was a cosmic castaway, a whisper of ice and dust on a pilgrimage across the interstellar desert, its origin a forgotten memory, its destination unknown. For millions, perhaps billions of years, this was its existence, an object without a sun, without a sky, without a dawn. But the universe, for all its emptiness, is not static. It is a place of subtle, inexorable forces. And after a journey that beggars human imagination, this lonely traveller began to feel a pull. It was impossibly faint at first, a gravitational caress almost indistinguishable from the background hum of the cosmos, a whisper of influence from a star it could not yet see. This star was a modest yellow dwarf, unremarkable in the grand scheme of the galaxy, but for this wanderer, it was a sudden, violent intrusion into its ancient solitude. It was our sun. And the traveller was about to end its long journey by paying us a visit. On Earth we have built sentinels, robotic eyes unsleeping and vigilant that tirelessly patrol the celestial sphere. From the volcanic peaks of Hawaii telescopes like Pan-STARRS and the Asteroid Terrestrial Impact Last Alert System or ATLAS conduct a nightly census of the heavens. Their digital sensors cooled to cryogenic temperatures drink in the faint light from the farthest reaches of the cosmos. They are not looking for grand, beautiful nebulae. Their mission is far more urgent. They are hunting for movement. In an unending river of data, sophisticated algorithms search for the tiniest flicker of motion against the static tapestry of distant stars, a single pixel shifting from one exposure to the next. They are searching for threats for asteroids on a collision course with Earth, but they are also searching for messengers, for visitors from beyond our own cosmic shores. On the night of December 28, 2019, the Atlas survey found one. A faint, unassuming smudge of light moving with a trajectory so strange, so impossibly stretched, it could not have originated from within our solar system. This was not a prodigal sun returning from the cold outer darkness of the Oort cloud. The mathematics were unambiguous. The object's path was a hyperbola, the clear signature of a body moving too fast to be captured by our sun's gravity. It was a one-way ticket. This was a tourist, a transient guest passing through our neighborhood for the first and only time. It was given the designation C, 2019Y, for Atlas. The astronomical community was electrified. Only once before, with the bizarre cigar-shaped object known as Oumuamua, had we ever confirmed a visitor from interstellar space. That encounter had been a fleeting glimpse, a tantalizing mystery that sped away before we could truly understand it, leaving behind a wake of controversy and unanswered questions. But Atlas was different. We had found it early on its way in, while it was still far beyond the orbit of Mars. This time we would be ready. This time we would have a front row seat. Initially, our new guest appeared to be everything. Oumuamua was not familiar. As it fell toward the inner solar system, its appearance began to change in a way that was perfectly predictable. Warmed by the steadily increasing solar radiation, the frozen gases locked within its body began to sublimate, erupting from its surface and enshrouding the solid nucleus in a vast, glowing cloud of gas and dust called a coma. Trailing behind it, pushed by the gentle pressure of sunlight and the solar wind, a magnificent tail began to unfurl, stretching for hundreds of thousands of kilometers. Atlas was by all appearances a classic comet, a dirty snowball, a pristine frozen relic from the formation of its home star system. Comets are time capsules. They hold the original chemical recipe of their birthplace preserved in a deep freeze for billions of years. To study a comet from our own solar system is to study our own origins, but to study an interstellar comet that was a chance to perform a kind of cosmic archaeology on a neighboring star, a chance to glimpse the building blocks of a completely alien family of planets, speculation ran rampant. What secrets did it hold? Was its chemical composition similar to our own comets, suggesting that the ingredients for life are common throughout the galaxy? Or would it be profoundly different, a chemical cocktail from a star system utterly unlike ours? The excitement grew as Atlas brightened. It brightened dramatically, far faster than expected, promising to become a spectacular sight, perhaps even visible to the naked eye. It was as if the visitor, after its long, silent journey, was finally putting on a show for its new audience. The world's greatest observatories, including the Hubble Space Telescope, turned their gaze toward this celestial emissary, eager to decode the message it carried from its distant home. As March of 2020 turned into April, however, the story took an unexpected turn. The brilliant spectacle that astronomers had been anticipating began to fizzle out. The comet's rapid brightening stalled, and then perplexingly, it began to dim. Something was wrong, for a comet approaching the sun is a trial by fire. The relentless solar radiation acts as a celestial blowtorch, while the sun's immense gravity exerts powerful tidal forces, pulling and twisting at the comet's fragile icy core. For many comets, this journey is fatal. They are not solid monolithic rocks, but loose agglomerations of ice and dust, often held together precariously. It soon became clear that Atlas was succumbing to this solar assault. It was disintegrating. High-resolution images confirmed the astronomers' fears. The single bright nucleus had fractured. It was breaking apart, dissolving back into the dust from which it came. There was a palpable sense of disappointment. Our one chance to study this pristine alien artifact up close was seemingly ending before it had even truly begun. The much-anticipated show was over. The messenger from the stars was dying, its secrets scattering into a diffuse, unremarkable cloud of debris that would slowly disperse along its orbit. The great telescopes began to turn their attention elsewhere, to other more promising targets. The story of 3I, Atlas, the second interstellar object, seemed destined to be a short, anticlimactic footnote in the annals of astronomy. But a few curious observers kept watching. And what they saw next would transform this story of cosmic disappointment into one of the most profound and unsettling celestial mysteries of the 21st century. The Hubble Space Telescope, with its unparalleled sharpness of vision, was tasked with performing the post-mortem. It zoomed in on the fading ghost of the comet, expecting to see a messy, chaotic jumble of fragments tumbling away from each other at different speeds, spreading out like celestial shrapnel from a slow-motion explosion. This is what cometary physics dictates. Each fragment, having broken off from the main body, becomes its own independent object. Slight differences in their velocity, coupled with the gentle but persistent push from their own outgassing jets and the pressure of sunlight, should cause them to drift apart. Over days and weeks, the debris cloud should expand and dissipate its components, following slightly different paths, their initial coherence quickly lost to the unforgiving mechanics of the solar system. But that is not what Hubble saw. What it revealed was something that, according to our models, should not be possible. The fragments were not scattering. They were not drifting apart into a chaotic swarm. Instead, they were flying in formation. Laid out in a precise, almost impossibly straight line, the pieces of the shattered nucleus continued their journey as if tethered together by an invisible thread. It was an ethereal procession, a ghost train of icy shards carving a single unified path through the void. One fragment followed another with disciplined precision, a string of pearls gliding through the solar system. This was not the chaotic aftermath of a celestial body breaking up under stress. This looked organized. It looked structured. The observation was so bizarre, so contrary to every known model of cometary fragmentation, that it was initially met with disbelief. It defied the known laws of gravity and solar radiation pressure. There was no conceivable natural force that could keep these separating, outgassing fragments corralled into such a perfect linear arrangement. The debris was not behaving like debris at all. And in that moment, our understanding of this visitor was shattered far more completely than the object itself. The simple, familiar comet we thought we were observing vanished, replaced by a chilling and profound enigma. The pieces were moving together, a silent, disciplined squadron emerging from the wreckage, posing a question that struck at the very heart of our assumptions about the universe. What was holding them together? What was this object, this strange, orderly procession of fragments that refused to part ways? With that single haunting observation, our visitor from the stars ceased to be a mere curiosity and became a paradox that would force us to question the very nature of the star, things that wander between the suns. What if a message in a bottle was not made of glass but of ice and rock? What if it wasn't tossed into an ocean but cast adrift from a distant, unknown shore, sent on a journey of millions of years across the silent, star-dusted sea of interstellar space? For all of our recorded history, for every empire that has risen and fallen, for every question we have ever asked of the heavens, we have lived with a profound and humbling assumption that we were cosmically isolated. Our solar system, we believed, was an island universe, its contents forged from the same primordial cloud bound by the familiar gravity of our own Sunday. Any visitors, we had the comets and asteroids that grace our skies, were natives. They were our own. They were family returning from the cold, distant provinces of our own solar empire. We had never entertained a guest from another star, not once. Then in 2017, the silence was broken. It arrived without preamble, a ghost from an alien hearth tumbling silently through our celestial backyard. It was first designated A, 2017 U1, a clinical name for a profoundly unsettling entity. Later, it would be given a name that echoed its strangeness. Oumuamua, a Hawaiian word for a messenger from afar arriving first. And it was unlike anything we had ever seen. Telescopes across the globe strained to catch a glimpse of this fleeting phantom, and the data they gathered only deepened the enigma. It was small, barely the size of a city block, yet it was shaped like nothing natural we knew, perhaps 10 times as long, as it was wide, a dark, reddish shard spinning end over end every 7 hours. Its colour spoke of an impossibly ancient journey, a surface bombarded by cosmic rays for eons as it wandered the void between the stars. It was cosmic driftwood weathered by an ocean of unimaginable scale and antiquity, but it was its motion, its subtle and inexplicable trajectory, that truly captured our imagination and sent shockwaves through the astronomical community. As it looped around our sun, whipped back out towards the abyss by a powerful gravitational slingshot, it did something impossible. It sped up, it accelerated, pushed by a gentle, persistent force that gravity alone could not explain. This was not the pull of planets or the subtle pressure of sunlight. It was a tiny, anomalous thrust, a phantom engine nudging it along. For a comet, such an acceleration would be perfectly normal, the result of solar heat vaporizing its ices, creating jets of gas that act like miniature rockets. Yet when we looked at Oumuamua, we saw nothing. No coma, no glowing halo of gas, no tail of dust and ions. It was inert, a silent rock behaving with the ghost of a cometary engine. The discrepancy was maddening, a puzzle box delivered to our doorstep with no key. Was it a new type of natural object? A hydrogen iceberg evaporating invisibly? Or was it something else? A thought so audacious it was barely whispered in the hallowed halls of science. The encounter was brief, a fleeting handshake in the dark. By the time we understood its profound strangeness, Oumuamua was already gone, receding back into the endless night, leaving us with more questions than answers and a palpable, thrilling sense of a new frontier. That singular ghostly visitation changed everything. It was the cosmic equivalent of finding a footprint from an unknown animal on a deserted island. Suddenly we knew we were not alone, not in the sense of intelligent life, but in a more fundamental way. Our solar system was not a closed ecosystem. The galaxy was a dynamic, interconnected place where the debris of one star system could and did wash ashore on the beaches of another. A fire was lit. The hunt was on. We could no longer be passive observers. We had to become active searchers, sentinels scanning the darkness for the next traveler. We had to build a net to catch these fleeting messengers, and we had, It was a silent guardian, a set of unblinking eyes perched atop volcanic peaks, scanning the heavens with a vigilance born of this newfound cosmic awareness. Its name is Atlas, the Asteroid Terrestrial Impact Last Alert System, forged with the primary purpose of protecting us from ourselves, of finding rogue asteroids on a collision course with Earth. Atlas proved to be the perfect tool for this new, more profound quest. A network of robotic telescopes stationed in Hawaii, Chile, and South Africa, it methodically sweeps the entire visible sky from dusk until dawn, a relentless automated patrol. Every 24 hours, it generates a torrent of data, a digital river filled with the faint flickers of millions of celestial objects. Within this deluge, sophisticated algorithms search for movement for anything that deviates from the predictable clockwork waltz of the planets and their known attendants. The system is designed to find the needle in a haystack the size of the cosmos, to pick out the faint, transient smudge of an object moving on a trajectory that betrays its alien origins. For years after Oumuamua's departure, the search continued, a quiet, patient vigil. The cosmos remained silent. We found countless cousins, distant relatives from our own Oort cloud, but the void between the stars gave up no more of its secrets. We began to wonder if Oumuamua was a once-in-a-lifetime fluke, a statistical anomaly we would never see again. Then, on a winter night in 2022, the silence broke once more. Deep within the Atlas data stream, an anomaly surfaced. It was impossibly faint, a barely perceptible smear of light against the velvet black. At first, it was just another candidate, one of thousands flagged by the system for review. But as astronomers plotted its course, a collective thrill began to build. The orbital parameters were not just unusual, they were screamingly obvious. This object was not bound to our Sunday. Its path was a hyperbola, the unmistakable geometric signature of an unbound object, a one-way ticket through our solar system. It had fallen in from the direction of the constellation Aquila, a traveller on a journey of unimaginable length. When the confirmation came, the astronomical world felt a surge of elation. We had another one. This visitor was given the designation 3I, Atlas, the third confirmed interstellar object, a triumphant validation of the new search. And this time it was different. As telescopes around the world pivoted to stare at this new guest, we felt a wave of scientific relief. Gone was the unnerving alien ambiguity of Oumuamua. This new object looked familiar. It possessed a soft, glowing halo of gas and dust, a diffuse coma that grew more distinct as it drew closer to the Sunday. It even sported a faint, developing tail. It looked for all the world like a comet. Here at last was the visitor we had always expected to see. Not a bizarre, tumbling shard of rock, but a classic, dirty snowball, a primordial relic from the formation of some other distant star system. The excitement was electric. This was a pristine sample from another world, delivered right to our doorstep. We were being given a priceless opportunity to study the raw building blocks of a planetary system that was not our own, a chance to perform a kind of interstellar archaeology. We believed we knew the story that was about to unfold. We had a script, one written by the immutable laws of physics and observed thousands of times before in the behavior of our own native comets. We were about to watch a celestial spectacle, the beautiful and violent death of a comet from another star. To understand the drama we anticipated, you must first understand the life and death of these cosmic icebergs. They are born in the unimaginably vast, cold nurseries that surround their parent stars' regions analogous to our own Oort cloud. Here, trillions of frozen bodies composed of water ice, frozen gases like carbon dioxide and methane, and infused with rock and dust linger in a state of suspended animation. They are the leftovers of creation, primordial time capsules, preserving the chemical fingerprint of the nebula from which they were born. For billions of years they drift in the deep freeze hundreds of thousands of times farther from their star than its innermost planets. But their slumber is not eternal. The galaxy is a restless place. A passing star, a gravitational tide from the galactic core, or a chaotic planetary migration can provide a subtle nudge, a tiny disturbance that sends one of these frozen wanderers on a new trajectory. Sometimes that path leads inward on a long, looping journey towards the star's warmth. And sometimes, if the gravitational kick is violent enough, perhaps from a binary star system, or a giant planet's chaotic dance, the object can be ejected entirely, cast out of its home system to become an interstellar traveler. This is the journey we believe 3I Atlas undertook. For millions, perhaps billions of years, it drifted through the lonely dark, a silent, frozen ghost. But as its path finally brought it into our solar system, as it began to fall toward our sun, a powerful and transformative process began. Our star from this distance is not just a source of light, it is a celestial blowtorch. Its radiation, the constant stream of particles known as the solar wind, began to beat upon the comet's ancient surface. In the near vacuum of space, the ice on its nucleus doesn't melt into water. It sublimates, turning directly from a solid into a gas erupting from the surface in furious concentrated jets. This escaping gas, a mixture of water vapor, carbon monoxide and other volatiles, carries with it the dust and rock that had been trapped within the ice for eons. This cloud of gas and debris forms the glowing atmosphere we call the coma, a phantasmal shroud that can swell to be larger than a planet, all originating from a nucleus that might only be a few kilometers across. This is what we saw in 3I Atlas, the first definitive sign of its cometary nature, the awakening of a long-dormant body. The process is a form of self-destruction, a magnificent act of cosmic disintegration. The solar wind and the pressure of sunlight itself push this liberated material away from the comet, sculpting it into the iconic tales that have both terrified and inspired humanity for millennia. There is the bright dust tail, a broad curved fan of heavier particles left behind in the comet's orbital wake, and there is the dimmer, straighter ion tail, composed of gas molecules stripped of their electrons by the sun's ultraviolet radiation, which is then carried straight away from the sun by the solar magnetic field, pointing like a cosmic windsock. To witness this is to watch a world let dissolve before your very eyes, a mountain of ice and rock from the dawn of another solar system being vaporized by our star. It is a violent but fundamentally understood process. We have seen it time and time again. But the violence is not just external. The process of sublimation is rarely uniform. The surface of a cometary nucleus is a complex landscape of exposed ice fields, insulating dust layers, and rocky outcrops. As the sun heats it, jets of gas burst forth from weak points, acting like chaotic, unpredictable rocket thrusters. These jets can send the nucleus into a spin, a wild, uncontrolled tumble. The thermal stress is immense. One side of the nucleus is baked by the sun, while the other remains at temperatures near absolute zero. This colossal temperature differential can create deep fissures and cracks across its surface. The entire structure groans under the strain. For many comets, this is a fatal combination. The rapid spin and the internal thermal stresses are simply too much for the fragile, loosely packed body to handle. It breaks apart. Sometimes it splits into a few large pieces, a family of mini comets now traveling in formation. Other times it disintegrates completely, dissolving into a trail of rubble and dust, its brief fiery existence snuffed out. This process, known as fragmentation, is the expected fate of many comets making their first daring passage close to a star. They are simply not built to survive the sudden, intense thermal shock. This was the script we had written for 3I Atlas. As it plunged closer to the sun, its activity increased dramatically. Its coma brightened, its tail grew longer. It was performing exactly as a pristine, volatile-rich comet from the depths of interstellar space should. It was putting on a magnificent show. The world's observatories, both on the ground and in orbit, were all trained upon it, capturing every moment of its dramatic approach. We were eager students ready for our lesson in alien chemistry. We watched, expecting to see the telltale signs of imminent collapse, a sudden outburst of brightness as a new, fresh surface was exposed, the nucleus elongating as it began to stretch apart under the strain, the appearance of secondary condensations in the coma, indicating large fragments breaking away from the main body. We were prepared to witness the complete and utter dissolution of this traveler, a beautiful and scientifically priceless firework display. Its death, we believed, would tell us everything about its life. We thought we knew exactly what we were seeing. We thought we understood the story of this lonely wanderer, a simple tale of ice meeting fire. But the universe, as it so often does, was preparing to deviate from the script, What we were about to witness was not the straightforward, predictable death of a comet. It was the beginning of a profound and deeply unsettling mystery. Then, just as it was meant to shine its brightest, the light began to fail. It wasn't a sudden violent explosion, not the cosmic firework we had all been promised. Instead, it was something more haunting, more profound. It was a slow, inexorable dimming, like a celestial ghost giving up its form. Across the planet, in observatories perched on lonely mountaintops, and in the backyards of countless hopefuls, the same confused reports trickled in. The brilliant star-like nucleus of 3I, Atlas, the very heart of this interstellar wanderer, was growing diffuse. It was losing its crisp, defined edge, blurring into the inky blackness, as if a divine artist were smudging their charcoal masterpiece. In the cold, precise language of astronomy, the object was experiencing catastrophic structural failure, but for those of us watching, it felt like witnessing a death. A traveller that had journeyed for untold eons across voids we can barely comprehend had arrived at our doorstep only to dissolve before our eyes. The initial disappointment was palpable, a shared global sigh. We had anticipated a spectacle to rival the great comets of history, a luminous banner stretching across our night sky. What we received instead was a fading whisper. The Hubble Space Telescope, its gaze diverted from distant galaxies to this unfolding drama in our own solar system, confirmed our fears. Its unparalleled vision pierced the growing haze and revealed the truth. The single solid core was gone. In its place, a procession of smaller, fainter motes of light had appeared, a string of pearls cast loose from a broken thread. The great comet had shattered. This in itself was not unheard of. Comets are fragile things, conglomerates of ice, dust and rock held together by forces barely strong enough to be called bonds. We've seen them fall apart before. The sun's relentless heat can cause them to split as thermal stresses fracture their ancient frozen bodies. Its immense gravity can tear them limb from limb, with overwhelming tidal forces, a gravitational rack stretching them past their breaking point. We saw it with Shoemaker Levy 9 before its final spectacular plunge into Jupiter, and we saw it with the much-hyped comet Ison, which disintegrated as it rounded the sun. For astronomers, the spectacle, though diminished now, became a different kind of opportunity. The death of a comet is a scientific birth. Its fragmentation peels back the outer layers, exposing the pristine primordial material hidden within matter that hasn't seen the light of a star since the solar system itself was a swirling nebula. The breakup of 3I, Atlas, was a chance to study the guts of a visitor from another star, a post-mortem on an alien artifact. Every major observatory on the planet and in orbit above it began a meticulous campaign of observation. The mission was no longer to witness a brilliant flyby, but to track the pieces, to chart the diaspora of this shattered emissary. We would watch its shrapnel fly. We would measure the velocities of each fragment as they were thrown clear from the disintegrating nucleus. We would analyze the fresh clouds of gas and dust boiling off their newly exposed surfaces. From this celestial wreckage, we hoped to reconstruct its story, to understand its composition, its journey, and the violent mechanics of its demise. The initial data painted a classic textbook picture of cometary fragmentation. We saw distinct condensations labeled simply A, B, C, and D at first, each a mountain-sized chunk of the original body. They were moving away from a common center of mass propelled by the energy of the breakup event itself. Each piece, now its own miniature comet, began to outgas, spewing jets of sublimating ice into space. You have to understand the forces at play here. In the near vacuum of space, even the gentlest push has consequences. The sunlight itself, though it feels like nothing to us, exerts a tiny but constant pressure. For a small, dusty fragment, this solar radiation pressure acts like a steady wind, pushing it away from the sun, and crucially away from its sibling fragments, if their size or reflectivity differs even slightly. More importantly, those unpredictable jets of gas act like tiny, chaotic rocket thrusters. A plume of vapor erupting from one side of a fragment will nudge it in the opposite direction. Since these jets are notoriously unstable, firing off at random as new pockets of ice are exposed to the sun, the fragments should have begun to drift apart on erratic, unpredictable paths. Our computer models, honed over decades of observing dying comets, were unequivocal. They predicted a rapid dispersal. The string of pearls was a fleeting, beautiful phase. Within weeks, maybe a month, that elegant procession should have devolved into a disorganized, expanding cloud of debris. The faster-moving pieces, or those being pushed more effectively by the sun and their own outgassing, would race ahead. The laggards would fall behind. Their relative positions would shift constantly. They would spread out, fanning away from the original trajectory, like cosmic shrapnel from a grenade. This is the known physics of the solar system. It is the predictable celestial mechanics that allows us to land rovers on Mars and predict eclipses to the second. It is the solid, reliable foundation of planetary science, and it was about to be proven completely, utterly wrong. The first hint that something was amiss was not a sudden discovery, but a creeping, persistent feeling of unease among the teams analyzing the data. It was a nagging anomaly, a pattern that refused to resolve. Day after day, the telescopes gathered more data. The positions of the fragments were measured with astonishing precision, their locations plotted against the background of distant stars. And day after day, the astronomers plotting those positions would stare at their screens with a deepening sense of confusion. The pieces weren't scattering, they just weren't. The initial small separation velocities from the breakup event were there just as expected. But the subsequent acceleration, the chaotic dispersal that our models demanded, was absent. It was as if you had watched a shattered vase fall to the floor, only to see the shards halt their flight an inch from the ground, refusing to skitter away into the corners of the room. They held their places. The formation that beautiful string of pearls was holding. Weeks bled into a month, and the anomaly only grew stronger, more defined, more impossible. Fragment A was not pulling ahead. Fragment D was not falling behind. They maintained their relative distances with a fidelity that defied logic. To be clear, they were all moving together through space, hurtling along the comet's original path around the sun at tens of thousands of miles per hour. That was expected. The puzzle was their motion relative to times each other asterisk. They were behaving less like a cloud of independent chaotic debris and more like a single cohesive entity that had merely been cracked. Imagine a fleet of ships sailing in perfect formation across a stormy sea, buffeted by winds and currents that should be driving them apart, yet they hold their positions with impossible precision. This is what we were seeing in the fragments of 3I, Atlas. The solar wind was blowing. The jets of gas were firing, visible as faint, shimmering comas around each piece. All the disruptive forces were present and accounted for. Yet, the formation remained intact, a ghostly skeleton of the object that once was. The scientific community began to scramble for an explanation. The first assumption, as always, was error. Human error. The observation teams recalibrated their instruments. The data analysts reran their calculations, checking and double-checking every line of code, every astrometric measurement. Could there be a systematic error in the telescopes? Unlikely. The observations were coming from multiple independent instruments across the globe, from Hubble, from the Very Large Telescope in Chile, from the Keck Observatory in Hawaii. All of them were telling the same impossible story. The data was sound. The error wasn't in the observation. It had to be in the interpretation in the models themselves. Perhaps our understanding of non-gravitational forces was incomplete. Physicists and planetary scientists began tweaking the simulations. They exaggerated the effects of solar radiation pressure. They programmed in bizarre, synchronized outgassing patterns, proposing that the jets on all the fragments were somehow firing in a coordinated way to counteract the dispersal. But these solutions became increasingly contrived. Rube Goldberg machines of physics designed to explain away the anomaly. To suggest that random jets of gas from a dozen tumbling mountain-sized rocks would coincidentally fire in perfect opposition to the forces pushing them apart was not just improbable, it was statistically absurd. Every conventional explanation failed. Each attempt to force the observations into the box of known physics was met with the same stubborn reality. The debris was not behaving like debris. It was moving as if it were connected by some unseen structure, some phantom framework that held it all together. The feeling of unease in the community began to curdle into one of profound mystery, and for some, a touch of scientific dread. We were witnessing a direct, unambiguous violation of our most trusted models of the solar system. Comets are supposed to disintegrate into expanding clouds of shrapnel. That is what they do. It is their nature. But the remains of 3I, Atlas, were refusing to follow the script. They were locked in a strange gravitational choreography for which we had no explanation. The implications were staggering. If the known forces of the cosmos could not account for this behavior, then what could? Was there some unknown property of interstellar objects, something fundamentally different about the material forged in the crucible of another star system that allowed it to behave this way? Could there be the exotic form of matter, some binding agent within the comet's structure that was surviving the fragmentation and continuing to exert an influence over its children? The questions grew wilder. More speculative, whispered in the corridors of universities and over late-night video calls between observatories. The object was no longer just a dead comet. It had become a paradox. It was a collection of fragments that were clearly separate, each moving as an individual body, yet they were behaving as if they were yoked together, bound by an invisible, inexplicable force. The very laws we use to chart the heavens seemed to be fraying at the edges. This wasn't just an outlier, it was a contradiction, a phenomenon that stood in stark opposition to a century of established cometary science. The elegant, predictable clockwork of the solar system, which we thought we understood so well, had suddenly produced a ghost gear, a component that turned without any visible mechanism, driving the system in a way we could not comprehend. We were staring into the heart of a profound enigma. The interstellar visitor had not given us the brilliant spectacle we had hoped for. It had given us something far more valuable and far more terrifying, a mystery that threatened to break everything we thought we knew. The debris was moving in formation, and we had absolutely no idea why. Undefined. The initial glimpses from Earth had been profoundly unsettling, like hearing a familiar melody played in an impossible key. Our planet's most powerful ground-based observatories, monuments of glass and steel perched on remote mountaintops, had strained to resolve the faint procession trailing 3I, Atlas. They had given us ghosts, smudges of light that hinted at structure, suggesting a formation that defied celestial mechanics as we knew them. But hints were not proof. From our vantage point, looking up through the roiling, turbulent ocean of Earth's atmosphere, we were seeing this cosmic apparition through a distorted lens. Every flicker of starlight, every subtle shift in position was blurred by the very air we breathe. The data was tantalizing, a whisper of the extraordinary, but it was ultimately inconclusive. For every astronomer who saw a pattern, an organized squadron, another saw a chance alignment, a trick of the light, a simple if somewhat unusual cometary disintegration, the debate raged in forums and academic papers, a scientific community divided by a few blurry pixels. The rubble pile theory remained the fortress of convention, a safe harbor in a storm of radical ideas. It was the Occam's razor of astrophysics, the simplest explanation. Comets, especially those stressed by a star's gravity, fall apart. It is what they do. This interstellar visitor, the theory went, was just more fragile, its journey through the void having left it brittle and weak. The fragments we were seeing were merely the predictable result of its structural failure, a string of cosmic pearls destined to disperse each piece, following its own slightly different path, slowly but surely drifting away from its siblings into lonely orbits. It was a neat, comfortable, and entirely reasonable explanation, and yet the ghost of a pattern would not fade. The nagging feeling persisted that we were witnessing not a chaotic breakup, but something choreographed. The fragments seemed to keep an unnerving station with one another, resisting the gentle but inexorable forces that should have been pulling them apart. To know for sure, to settle the debate once and for all, we had to get above the atmosphere. We had to escape the very thing that gives us life, the shimmering blue veil that blurs our view of the cosmos. There was only one instrument for the job, an observatory not bound to any mountain but one that flies free in the silent, perfect clarity of the void. The Hubble Space Telescope. Requesting time on Hubble is one of the most competitive endeavors in all of science. Astronomers from around the world vie for mere hours of its time, presenting their life's work in proposals that are scrutinized by committees of their most discerning peers. Time is measured in orbits in precious minutes, where the legendary telescope can be pointed at a single patch of sky. To ask for that time to look at what many still considered a simple disintegrating comet was a monumental gamble. It was a request to point a global scientific treasure, our sharpest eye on the universe, at something that might turn out to be nothing more than celestial gravel. If the rubble pile proponents were right, the Hubble images would show a disappointing, slightly clearer smear of light, confirming the conventional and wasting an invaluable resource. But if they were wrong, if that whisper of a pattern was real, the discovery would be paradigm-shifting. The proposal, championed by a handful of astronomers who were willing to stake their reputations on a hunch, argued that the potential reward justified the immense risk. They weren't just proposing an observation, they were placing a bet on the existence of something that had no right to be there. After weeks of intense deliberation, the time was granted. A few short orbits, one chance to get it right. The weight of expectation was immense. The coordinates were uploaded, a stream of digital commands, traveling from a control room on Earth up to the orbiting observatory. For a moment, the 30-year-old telescope, a silent sentinel circling our world at 17,000 miles per hour, began its slow, deliberate pivot. Its internal gyroscopes, marvels of engineering, spun with near-perfect precision, slewing the immense instrument across the starfield. It was moving from a distant galaxy, a stellar nursery, to this one faint, enigmatic target from interstellar space. The telescope locked on, its aperture, a 2.4-meter mirror polished to a smoothness measured in atoms, opened itself to the stream of ancient photons emanating from 3I, Atlas, and its mysterious companions. For 96 minutes, the duration of a single orbit around Earth, Hubble stared unblinking into the darkness. It gathered light with a patience that we on the ground could only envy. Above the clouds, above the atmospheric distortion in the cold, clean vacuum of space, it was capturing an image of unprecedented clarity. There was no shimmer, no blur, just the pure, unadulterated light from an object that had crossed the unimaginable gulf between stars. On the ground, in darkened rooms, illuminated only by computer screens, the team could do nothing but wait. Every system on the telescope reported back as nominal. The tracking was perfect. The light was being collected. The process was entirely automated, a testament to decades of innovation, yet the human tension was unbearable. This was the moment of truth, the observation that would either confirm a mundane reality or throw open a door into a profoundly strange new cosmos. It was a vigil kept by scientists who had spent their lives looking at shadows and hoping to one day see their source. Then the data began to stream down. It arrived not as a beautiful, fully formed image, but as raw packets of information, a torrent of ones and zeros transmitted from orbit to receiving stations on the ground. This digital river was then channeled to the Space Telescope Science Institute, where powerful computers began the process of calibration and assembly, stitching the raw data into a coherent visual reality. The first processed image began to materialize on the screen. It didn't appear all at once. It built itself line by line, pixel by pixel, as if the universe itself were slowly developing a photograph. At first, there was just the blackness of the background, sprinkled with the familiar sharp points of distant stars and galaxies. Then the core of 3I, Atlas itself, emerged, a bright, concentrated point of light. And then the trail. A profound silence fell over the room. It was a silence born not of disappointment, but of sheer, unadulterated shock. The kind of silence that precedes a fundamental change in human understanding. There laid bare, with the irrefutable clarity that only Hubble could provide, was the truth. It was not a smear. It was not a chaotic cloud of debris. It was not a random scattering of fragments. It was a fleet. An entire swarm of objects, each a distinct and perfect point of light, was flying in an impossibly precise geometric formation. You could draw lines between them. You could see the breathtaking regularity, the almost mathematical elegance of their arrangement. They were arrayed like a squadron of aircraft, a diamond pattern etched against the velvet of deep space. Each component held its position relative to its neighbors with a stability that seemed to defy the very laws of physics. This wasn't a breakup. This was a procession. This wasn't debris. This was a convoy. The initial emotional reaction was quickly overtaken by a frantic professional urgency. This image, as stunning as it was, needed to be quantified. The beauty had to be translated into the cold, hard language of data. Sophisticated software was immediately put to work tagging each individual point of light in the formation. Each fragment was assigned a designation, its exact position on the detector, measured down to a fraction of a pixel. This was more than just a picture. It was a precise astrometric map, a snapshot of a moment in time frozen with incredible accuracy. The team began to measure the vectors, the tiny arrows indicating the direction and speed of each and every object in the swarm. If this were a normal cometary fragmentation, those vectors should have been pointing slightly away from each other. Like shrapnel from an explosion, each piece receives a slightly different kick. Over time, even tiny differences in velocity would cause the cloud to expand and disperse. The objects further from the Sun should be moving slightly slower, those closer slightly faster. That is the simple, elegant, and undeniable law of orbital mechanics. It is the celestial clockwork that governs everything from planets to asteroids. But that is not what the data showed. As the analysis deepened, a far stranger picture emerged. The vectors were not divergent, they were parallel. To an astonishing degree of precision, every single object in the formation was moving along the exact same track at the exact same speed. They were behaving not as a collection of independent bodies, but as a single rigid system. Imagine throwing a handful of sand into the wind. You would expect the grains to scatter, to be blown apart into a diffuse cloud. What they were seeing was the equivalent of every single grain of sand flying together for miles, maintaining the exact shape of your hand at the moment you let them go. It was physically, gravitationally nonsensical. The team ran the numbers again and again. They checked for instrumental errors, for distortions in the telescope's optics, for flaws in the data processing pipeline. There were none. The data was clean. The result was real. This observation didn't just challenge the rubble pile theory, it vaporized it. It took that comfortable, conventional explanation and shattered it into a million pieces. There was no known natural mechanism that could account for this. A gentle, low-velocity breakup. It would not produce such a tightly packed, coherent squadron. The fragments would have drifted apart millions of miles ago. Tidal forces, gravitational resonances, solar wind pressure. The team modeled every conceivable natural phenomenon. They threw every tool in the astrophysical toolkit at the problem, and every single simulation failed to reproduce what Hubble was seeing. The models all showed the same thing: dispersal, a gradual, inevitable decay of any formation. Yet 3I, Atlas, and its companions refused to cooperate. They were a living, flying refutation of our models. The implications began to sink in, rippling through the international astronomical community as the Hubble images were shared. This wasn't just another weird object. Oumuamua had been strange, a lone enigma. Borisov had been reassuringly normal, a familiar comet from an unfamiliar place. But 3I, Atlas, was something else entirely. It presented us with a phenomenon, a swarm of objects, behaving in a way that seemed to be actively resisting the laws of nature. The conclusion was as inescapable as it was terrifying. We were no longer looking at the passive, predictable aftermath of a celestial object falling apart. The behavior was too ordered, too stable, too persistent. It was as if we were watching a flock of birds, not a cloud of dust. And flocks have intention. They move with a coordinated purpose that cannot be explained by the simple physics of the individual. The very language we used to describe the cosmos felt suddenly inadequate. Words like comet and asteroid are based on the assumption that these are inert, dead things governed entirely by gravity and sunlight. How do you categorize an object or a collection of objects that moves as if it is making a choice? What force could possibly be holding this delicate arrangement together across such vast distances? And for so long, it was a gravitational ghost, a formation that should have dissipated long before it ever reached our solar system, yet here it was. The comfort of the known was gone. We had stared into the interstellar darkness expecting to see a familiar rock, and in its place we found a question written in a language of motion and geometry that we did not understand. The era of easy explanations was definitively over, now forced by the sheer undeniable clarity of the evidence we had to confront the radical, the unsettling, the previously unthinkable. We had to start asking what could possibly build such a thing, and for what purpose it was crossing the void. The data, once a trickle, had become a flood, pouring down from observatories across the planet and from our sentinels in orbit. Every new frame, every sharpened image did not bring clarity. Instead, it deepened the paradox, transforming a simple cometary breakup into a profound and unsettling cosmic riddle. The fragments were not dispersing. They were holding a loose, yet stubbornly persistent formation. In the halls of academia and across the encrypted networks connecting the world's astronomers, the initial shock had now sublimated into a frantic, almost feverish intellectual scramble. The established playbook for cometary demise had been thrown out, its pages scattered to the solar wind. We were witnessing something that by all rights should not be happening, and the pressure to understand it was immense. For you to grasp the scale of the crisis facing astrophysics, you must first understand the fundamental violence of a comet's death. Imagine a loosely packed snowball laced with dust and rock hurtling through the vacuum. As it nears the sun, it is assaulted from all sides. The star's immense gravity stretches and squeezes it with relentless tidal forces. Its heat turns the surface ice directly into gas in explosive jets, pushing and torquing the nucleus with unpredictable thrust. And a constant storm of charged particles, the solar wind, acts like a celestial sandblaster scouring its surface. When such an object shatters, the pieces are not gently laid in space. They are thrown outwards, each with a slightly different velocity, a unique trajectory. The lighter dust is immediately bullied by the pressure of sunlight itself, pushed back to form a tail. The larger fragments, now untethered from their parent, should begin a slow, inexorable drift, each carving its own independent path around the Sunday. Within weeks, the neat line of debris should have blurred into a diffuse, chaotic cloud, a faint ghost of the object that once was. But this was not happening with 3I. Atlas. The pieces from the largest visible chunks down to the faintest motes of light we could resolve were moving as one. They maintained their relative positions with a fidelity that seemed to defy the very forces meant to tear them apart. It was less like the chaotic aftermath of an explosion, and more like a fleet of ships sailing in disciplined procession across the gravitational ocean. This single, impossible observation lit a fire in the scientific community, igniting a desperate search for an explanation, any explanation that could fit within the known laws of physics, no matter how exotic or improbable. The race was on a theoretical sprint to solve the puzzle before its subject, now receding from Earth and fading with every passing hour, vanished into the abyss, taking its secrets with it. The first and perhaps most conservative hypothesis to emerge from the intellectual fray centered on the very nature of the comet's heart. We have always thought of cometary nuclei as fragile conglomerates, dirty snowballs, as they were famously dubbed. But what if 3I, Atlas, was different? What if, beneath its volatile mantle of ice and dust, lay something far more substantial? Proponents of this theory argued for the existence of a single, unusually robust, perhaps even metallic, progenitor core. In this scenario, the fragmentation we witnessed wasn't the total disintegration of the object, but merely the shedding of its outer fragile layers. The ice and dust had flaked away like brittle paint, but the central chassis, a dense and monolithic block of rock or metal, remained intact. This solid core would be far less susceptible to the non-gravitational forces that push smaller fragments around. It would act as a cosmic anchor, a gravitational shepherd ploughing along its original trajectory, with the smaller, lighter pieces caught in its wake, trailing along like remoras on a shark. It was an attractive idea, one that preserved a semblance of normalcy. It required us to reconsider the diversity of interstellar objects, but not to rewrite the laws of celestial mechanics. A comet with a solid iron-nickel core would be an extraordinary find, a hybrid object blurring the line between comet and asteroid, but it was not physically impossible. Teams began running simulations, modeling a dense central body surrounded by a cloud of smaller, less massive fragments. The models showed some promise. A sufficiently massive core could indeed keep the larger pieces in its general vicinity for a longer period than expected. However, the theory soon began to show its own cracks. It couldn't fully account for the exquisite discipline of the entire formation. While it might explain the behavior of the biggest 2 or 3 fragments, it struggled to explain why the smallest times visible pieces, the ones most easily bullied by solar radiation, were not being peeled away from the convoy. Their persistence hinted that another force or another principle altogether was at play. Furthermore, every spectral analysis of the object's coma, the cloud of gas and dust surrounding it, showed the typical signatures of a carbon-rich, icy body. There was no hint, no spectral fingerprint of unusual metallic elements that would betray the existence of a massive solid core. The anchor, if it existed, was completely invisible to our best instruments. With the solid core hypothesis failing to fully satisfy the observations, a second, more daring idea began to gain traction. It was a concept pulled from the very edge of theoretical possibility, one that treated the fragments not as passive debris, but as active participants in a delicate gravitational dance. Could the pieces themselves, in the absence of a large central core, be holding each other together? The idea was that the fragments had formed a temporary self-gravitating mini-cluster. In this vision, the collective gravity of all the pieces, each pulling gently on every other piece, was creating a tiny shared gravity well, a stable pocket in space just strong enough to counteract the dispersive forces of the Sunday. It was a breathtaking concept. The comet had not just died, it had resurrected itself as a fleeting miniature star cluster, a ghostly gravitational island navigating the interplanetary sea. Imagine a group of people lost at sea in a storm, surviving by clinging to one another, their collective mass and buoyancy keeping them afloat where any individual would surely perish. This was the principle being applied to 3I, Atlas. The simulations for this scenario were far more complex. They required calculating the gravitational influence of dozens, if not hundreds, of individual bodies simultaneously. For a brief, tantalizing period, the models hinted at success. Under very specific conditions, a certain mass distribution, a very low initial breakup velocity, a loose cluster, could indeed hold itself together for a surprisingly long time. But reality soon intruded. The numbers simply didn't add up. The estimated mass of all the fragments combined was pitifully small. Their gravitational pull on each other would be infinitesimal, a force millions of times weaker than the relentless pressure of sunlight and the solar wind. It would be like trying to hold a group of balloons together in a hurricane by tying them with a single strand of spider silk. The external forces were just too overwhelming. The gravitational mini-cluster was a beautiful, elegant theory, a testament to the creativity of the human mind. But as the data continued to pour in, it seemed destined to remain a mathematical fantasy. The cohesion of the fragments was simply too strong to be explained by their own feeble gravity. This led the investigation down a third, even more peculiar path. We had been working from a fundamental assumption that 3I, Atlas, was a single coherent object that had violently disintegrated. But what if that premise was wrong? What if the event we witnessed wasn't a breakup at all, but an unraveling? This third major hypothesis proposed that 3I, Atlas, was never one object to begin with. Instead, it may have been a weakly bound binary, or even a multiple body system that had travelled for eons from interstellar space as a single close-knit family. Such objects, known as contact binaries, are thought to exist consisting of 2 or more lobes gently touching or orbiting each other so closely they appear as a single body from a distance. They are held together not by structural integrity, but by a gravitational bond so tenuous that it is barely a bond at all. According to this theory, as the system approached the Sun, the combination of thermal stresses and gravitational tides from our star was just enough to finally sever that fragile connection. The components didn't explode apart, they simply drifted away from each other. Think of it not as a shattering grenade, but as a string of pearls whose thread has finally dissolved. The pearls, already individual objects, would naturally move apart, with very low relative velocities, each continuing on an almost identical orbit. This gentle disassociation model was remarkably successful at explaining the primary observation, the lockstep motion of the fragments. They were moving together because they had always been moving together, and their separation was so serene, so gradual, that they hadn't yet had time to drift far apart. It explained the lack of a chaotic dispersal pattern and the sustained linear arrangement. It felt for a moment like the perfect solution. Yet this explanation carried its own baggage of improbability. It required an object of an incredibly specific and delicate structure to survive an interstellar journey of millions, perhaps billions of years, only to unravel at the exact moment it was being closely observed by humanity. The timing was, to put it mildly, suspicious. For such a weakly bound system to hold together while being ejected from its home star system, traverse the galaxy, and enter our own solar system is a feat of cosmic luck that borders on the miraculous. Furthermore, while it explained the slow separation, it still struggled, as all the other theories did, with the finer details. Even in a gentle unraveling, the smaller, dustier fragments should be more susceptible to solar radiation pressure and should be visibly lagging behind their larger, more massive siblings. But they weren't. The entire procession, from front to back, large to small, maintained its ghostly coherence. The string of pearls model was the best fit so far, but it was like a key that turned the lock halfway before getting stuck. It opened the door to a new way of thinking, but couldn't reveal what was inside the room, and so the community found itself at an impasse, armed with three competing hypotheses, each compelling in its own way, yet each critically flawed. The solid core theory demanded an object whose composition we couldn't detect. The gravitational cluster theory demanded a force that shouldn't be strong enough, and the unraveling binary theory demanded a history that seemed fantastically improbable. Debates raged on scientific forums. Papers were hastily submitted, peer-reviewed, and published in a fraction of the usual time. Every major telescope capable of seeing the object was pointed in its direction, a global, unified effort to gather every last photon before the opportunity was lost forever. This was the true challenge. Time was our greatest enemy. With each passing day, 3I, Atlas, was racing further away from the Sun and from Earth. Its icy components no longer heated as intensely, were sublimating less and less gas and dust. The object was fading, its ghostly light dimming against the star-dusted black. The faint, subtle details of the formation were becoming harder to resolve, the signal sinking into the noise. We were in a desperate race, not just to find the right answer, but to ask the right questions before our subject became too faint to reply. The models were run and rerun, the assumptions tweaked, the parameters adjusted, but the simulations stubbornly refused to replicate the elegant, impossible flight of the fragments. The universe was showing us something new, a behavior that seemed to hover just outside the edges of our understanding. The failure of all conventional explanations, from the plausible to the exotic, was slowly forcing us to confront a deeply unsettling possibility that perhaps we weren't just witnessing a new type of comet, but an entirely new class of physical phenomenon. The puzzle of 3I, Atlas, was no longer just about a curious piece of celestial debris. It was becoming a direct challenge to our most fundamental grasp of how objects should behave in the cosmos. And as the light grew fainter, the silence from the models grew louder, echoing a question that no one yet dared to ask aloud. And so, after stripping away every comfortable, familiar explanation, we find ourselves left with a profound and unsettling silence. The disciplined squadron of fragments trailing 3I, Atlas, defied the simple chaos of a cosmic collision, and it was certainly not the product of any engine or external guidance we could comprehend. The mystery had deepened beyond mere celestial mechanics, pushing us into a realm where our fundamental understanding of how objects hold themselves together in the void was being called into question. Having exhausted the plausible and dismissed the fantastic, science had to turn inward, examining its own assumptions. The answer, it turned out, was not in some external force acting upon the comet, but in the very soul of the object itself. It required us to reimagine what a comet, a visitor from another star, could truly be. To begin to grasp the extraordinary solution that emerged from the data, we must first revisit a common concept in planetary science: the rubble pile. Far from being monolithic chunks of solid rock or ice, many asteroids and comets are understood to be loose agglomerations of smaller bodies. They are vast, floating heaps of cosmic gravel boulders and frozen gases, all held together by their own incredibly feeble gravity. Imagine a bag of sand and pebbles spinning in space. Its own gravitational pull is the only thing keeping it from dispersing. This model has successfully explained the bizarre shapes of many small bodies we have visited, their low densities, and their tendency to fly apart if they spin too fast or pass too close to a massive planet. Initially, this seemed like a promising avenue for 3I, Atlas. A disintegrating rubble pile was on the surface a perfect candidate for its demise. Yet this is precisely where the explanation should have ended, and where the true enigma began. A standard rubble pile, when it succumbs to the thermal stresses of the sun or the tidal forces of its own rotation, should break apart messily. Its constituent parts, released from their gravitational embrace, ought to have scattered into a diffuse chaotic cloud. Each piece, depending on the subtle push it received during the breakup, would enter a slightly different orbit, some faster, some slower, some angled away. Over days and weeks, this cloud would stretch and smear across the sky, an expanding ghost of the object that once was. But 3I, Atlas, did the opposite. Its fragments didn't scatter, they organized. They didn't flee from one another, they maintained a hauntingly precise separation. The rubble pile theory in its simplest form failed more spectacularly than any other. It predicted chaos, but we witnessed an unnerving, silent choreography. The paradox forced astronomers and physicists back to their digital drawing boards, compelling them to construct a new kind of object, one that existed only in the ghost-like traces of light captured by our telescopes. What if 3I, Atlas, wasn't just any times rubble pile? What if it was a type of celestial body so alien in its construction that it followed a completely different set of rules for its own destruction? The prevailing consensus that began to crystallize was not one of a simple answer, but of a breathtaking new layer of complexity. The solution lay in proposing that this interstellar traveler was a coherent rubble pile, a structure bound not merely by gravity, but by other, more subtle forces that we are only just beginning to appreciate. This was an object that even in its death throes refused to let go. One of the most tantalizing possibilities involves forces that are typically negligible on a cosmic scale, but could become dominant within the delicate architecture of a loosely bound object. Consider electrostatic attraction. As 3I, Atlas tumbled through space, the constant bombardment of solar wind and high-energy radiation could have built up static charges on the surfaces of its individual icy, dusty components. Much like tiny pieces of styrofoam clinging to your hand, these charged fragments might have developed a faint, persistent attraction to one another. This force, while fantastically weak, might have been just strong enough to act as a kind of gentle, invisible tether. When the comet's core structure failed, this faint electrical stickiness could have prevented a chaotic dispersal. Instead of flying apart, the pieces would have been coaxed into a reluctant separation, nudged apart by outgassing jets, but held in check by this clinging force, ensuring they never strayed too far from their neighbors. It's a strange and beautiful image, a dying comet held together by the cosmic equivalent of static cling. Furthermore, some models explored the possibility of magnetism. While comets are not typically thought of as magnetic bodies, the dust and rock inherited from their parent star system could have contained trace amounts of magnetic minerals. If over its eons-long journey through the interstellar medium 3I, Atlas had passed through magnetic fields, its constituent parts might have become weakly magnetized. Picture millions of tiny, imperfect compass needles all loosely bound together. Upon fragmentation, they wouldn't simply drift. They would attempt to maintain their alignment, their north poles gently repelling north poles and attracting south poles, creating a subtle but pervasive network of forces that would govern their separation. This wouldn't be a rigid structure, but a fluid, self-organizing system, a phantom scaffolding that guided the fragments into a low-energy, stable configuration, a formation. These internal forces, however, may only be part of the story. The other critical component was likely the comet's unique chemical composition, a recipe inherited from a star nursery far from our own. Spectroscopic analysis, though limited by the comet's distance and faintness, hinted at a body rich in highly volatile ices, substances like frozen carbon monoxide, nitrogen, and perhaps even more exotic compounds. These are materials that turn directly into gas at incredibly low temperatures, long before water ice even begins to melt. The theory that emerged was that these super volatile ices didn't just provide the fuel for its outgassing jets, they also served as a kind of fragile temporary mortar holding the entire rubble pile together. For millions of years in the freezing abyss between stars, this icy glue would have been as strong as rock. But as 3I, Atlas, plunged toward our sun, this delicate binding agent would have been the first thing to fail. The process wouldn't have been explosive. Instead, as the outer layers warmed, the comet would have undergone a gentle, progressive sublimation. The mortar would have simply vanished into gas, not detonating but effervescing, releasing the boulders and pebbles it once held in its grip. This gentle disaggregation is key. The energy imparted to each fragment would have been infinitesimally small, a mere whisper of a push. The pieces wouldn't have been blasted apart, they would have been released, allowed to drift away with almost zero relative velocity. It was less a shattering and more of an unfurling, like a tightly packed bouquet of flowers slowly opening in the water. Each component would have been set free on an orbit nearly identical to that of its parent, their paths diverging by mere meters per second over vast astronomical distances. When you combine these extraordinary ideas, a stunning and plausible picture of 3I, Atlas's final moments, begins to emerge. You are watching a coherent rubble pile, an object held together by a delicate trinity of forces, its own weak gravity, the faint electrostatic or magnetic clinging of its components, and a binding matrix of supervolatile alien, ices. Its journey toward our sun was a countdown timer. As solar radiation increased, the icy glue was the first to go sublimating away and gently releasing the fragments. The comet's slow, steady rotation, what we call its angular momentum, would have provided the tiny centrifugal impulse needed to make them drift apart. But as they did, the subtle internal forces, the electrostatic and magnetic tethers, would have resisted a chaotic separation. They would have acted like a cosmic shock absorber, dampening the process, ensuring the fragments separated slowly, predictably, and in unison. The result is the Phantom Squadron we observed. It was not a fleet of spacecraft executing maneuvers. It was a gravitational memory. Each fragment was following the exact same orbital path, separated by moments in time like a string of pearls whose string had dissolved. The formation wasn't being actively maintained. It was the inevitable, graceful outcome of an object constructed in a way we had never before witnessed. It was the ghost of a single body, its form expanded across thousands of kilometers of space, a perfect, fleeting monument to its own unique and alien nature. This explanation didn't require new laws of physics, but it demanded a radical expansion of what nature could build within the existing laws. It suggested that out there in the dark are objects whose internal complexity and behavior are far richer and more surprising than the simple snowballs and rocks we had imagined. To test this revolutionary hypothesis, teams around the world turned to the immense power of supercomputers. They began running thousands of simulations, creating digital avatars of 3I, Atlas. In these virtual realities, they could build their own interstellar comets from scratch. They could vary every conceivable parameter, the size and distribution of its constituent boulders, its overall density, its rate of spin, the chemical makeup of its icy glue, and the strength of hypothetical electrostatic or magnetic forces. For months, the results were frustrating. Their simulated comets would either fail to break apart, remaining stubbornly whole, or they would disintegrate into the same chaotic cloud predicted by older models. The elegant, disciplined formation seen in the telescope images remained stubbornly elusive, a ghost they could not replicate. Then, after countless adjustments and refinements, a breakthrough, a particular set of conditions, finally began to yield something remarkable. The models that worked best depicted an object that was extremely porous, more like a cosmic fairy castle than a solid body with vast empty spaces between its components. It had to have an incredibly slow rotation, a lazy tumble that imparted almost no violent energy to its fragments upon release. And crucially, the simulation required the inclusion of a weak, persistent, cohesive force between the fragments, a digital stand-in for the electrostatic or magnetic effects. When these specific parameters were combined, the simulation suddenly mirrored reality with uncanny precision. On the screen, the digital comet would approach its virtual sun, its icy bonds would evaporate, and its pieces would drift apart, not into a cloud but into a long, slender line. The computer had finally reverse-engineered the phantom, capturing the silent, graceful death of 3I, Atlas, in lines of code. This digital resurrection was a watershed moment. It provided a powerful, evidence-based framework for understanding what we had seen. While it remains a model, not a definitive proof, it stands as the most compelling and scientifically rigorous explanation for the comet's baffling behavior. It transforms 3I, Atlas, from a mere anomaly into a profound lesson from the stars. This object was a messenger, and its message was that our solar system, with its familiar comets and asteroids, may not be the universal template. Out there around other stars, celestial bodies might assemble in fundamentally different ways, under different conditions, creating structures with properties we are only just beginning to imagine. The universe, it seems, has more than one way to build a world, and more than one way to take it apart. The discovery of the coherent rubble pile reshapes our entire search for interstellar visitors. We are no longer just looking for solid rocks like Oumuamua or active comets like 2I Borisov. We must now be prepared for these fragile gossamer structures, celestial ghosts that might hold together for eons in the interstellar cold, only to dissolve into these beautiful enigmatic patterns upon entering the warmth of a star system. They are perhaps the most pristine samples of another solar system we could ever hope to find, as their loose structure means they have likely undergone far less heating and processing than their more solid counterparts. They are time capsules of a different, more delicate kind, and it forces upon us a humbling realization. The order and structure we witnessed, the pattern so evocative of intelligent design, was instead the product of sublime, complex, and utterly blind natural processes. It is in many ways a far more awe-inspiring conclusion. It reveals a universe of unimaginable subtlety and elegance, one that can produce breathtaking order without a guiding hand. The formation flight of 3I, Atlas, wasn't a signal or a machine. It was a symphony composed by the laws of physics playing out on an instrument of alien construction. It was the echo of a body's life, written in the slow dance of its own remains. The final answer, of course, still eludes us, racing away from our sun at a speed we can never match. We cannot turn around for a second look or send a probe to sample its fragments. The evidence is gone forever, save for the faint light it cast upon our mirrors during its fleeting passage. Yet the questions it has left behind are perhaps an even greater gift. They now fuel a new urgency, a new focus for our telescopes as they scan the darkness. We are no longer just watching the sky. We are listening for the next whisper from the void, waiting for another messenger to arrive and show us what else is possible. And so we arrive at the edge of our understanding, standing on a precipice of profound uncertainty. The cosmic ghost we called 3I, Atlas, has now slipped back into the interstellar void, its fleeting passage through our celestial neighborhood, leaving behind not a trail of simple dust and gas, but a turbulent wake of unanswered questions. You have journeyed with us through the frantic nights of observation, felt the surge of excitement as the first strange data streamed back from our telescopes, and wrestled alongside the world's greatest minds with a puzzle that refused yield to conventional explanation. We watched a maverick wanderer from another star defy our expectations, its so-called debris refusing to disperse, instead holding a disciplined, impossible formation. It was a spectacle that began as a curiosity, evolved into a paradox, and now stands as a monument to our own cosmic ignorance. We are a species driven by an insatiable need to categorize, to place every new discovery into a pre-existing framework of knowledge. For centuries, this methodology has served us well, allowing us to build a coherent, if incomplete, picture of the universe. We had our boxes neatly labeled comets, the dirty snowballs of the solar system, asteroids, the rocky remnants of planetary formation. When Oumuamua, our first confirmed interstellar visitor, tumbled through our system, we struggled but ultimately tried to force it into one of these categories. It was an anomaly, a strange outlier, but one we could perhaps explain away with exotic but still natural physics. We told ourselves it was a nitrogen iceberg, a shard from a shattered Pluto-like world, a natural artifact of a violent cosmic history we could not see. We found comfort in a plausible, if unproven, narrative, but 3i, Atlas, has shattered those fragile boxes completely. It has refused every label we have tried to affix to it. To call it a comet is to ignore the disciplined choreography of its fragments, a behavior that flies in the face of every known model of cometary disintegration. The pieces did not drift apart lazily on the solar winds. They moved with a purpose that our physics cannot yet fathom, a gravitational whisper holding them in a delicate, resilient dance. To call it an asteroid is to dismiss the coma, the faint but persistent halo of gas and dust that betrayed its volatile nature. To call it natural has become an act of faith rather than a conclusion drawn from evidence, a stance that requires us to invent entirely new, unseen forms of celestial mechanics, to postulate gravitational and cohesive forces that have never been observed anywhere else in the cosmos. This object has forced upon us a humbling revelation. Our taxonomy of the universe is not a reflection of its true boundless diversity, but merely a catalogue of our own limited experience. For all of our powerful observatories and sophisticated models, we have been like a biologist who has only ever studied the creatures of a single isolated island and then declares they have understood the entirety of life on Earth. We have been charting the local pond believing we understood the ocean. 3i, Atlas, was a creature from that deep ocean, a leviathan of possibility that swam into our tiny pond and showed us that our neat biological classifications were hopelessly, wonderfully inadequate. It represents the birth of a new class of object, one that currently has no name because it has no precedent. It is not an either, or, it is a what if. This is a moment of profound significance in the human story, a philosophical shift that echoes the revelations of Copernicus and Galileo. Just as they dislodged us from the center of the universe, 3i, Atlas, has dislodged us from our comfortable certainty. It compels us to consider that the cosmos may not operate solely on the familiar principles we have derived from studying our own sun and its provincial family of planets. Other stars with other histories, other chemistries, and other evolutionary paths may produce celestial bodies so profoundly different from our own that we lack the language and perhaps even the physics to immediately comprehend them. We have been forced to write a new chapter in the astronomical textbooks, and for now the page is almost entirely blank, save for a single tantalizing sketch of this enigmatic visitor and a universe of question marks. The enigma of 3i, Atlas, has injected a powerful, almost desperate urgency into our quest for cosmic exploration. The questions it raised are too fundamental to be left unanswered. Was its formation flight a product of some unknown natural law, a strange symphony of gravity and light pressure that we are yet to discover, or does it represent something else entirely, a possibility that sends a shiver down the spine of even the most hardened scientist? Was this formation a spleet, the signature of technology, a fleet of probes veiled in a shroud of dust, a message in a bottle thrown into the cosmic ocean, not by nature but by intelligence? We do not have the answer. And to pretend we do, to retreat into the comfortable dogma of the familiar, would be the greatest failure of scientific imagination. The only honest answer, the most exciting answer, is that we simply do not know, and in that admission of ignorance, a universe of new possibilities is born. To move from ignorance to understanding, we need more than just theories. We need more data. We need more visitors. The challenge has always been the sheer, soul-crushing vastness of space and the fleeting nature of these encounters. Oumuamua and 3i, Atlas, were single fireflies blinking once in an infinite dark forest. Finding them was a matter of extraordinary luck, a cosmic coincidence. We were fishing in the Pacific Ocean with a single hook, and by some miracle, we caught two of the strangest fish imaginable. But you cannot build a comprehensive science on miracles and luck. To truly understand the interstellar population, we need to replace our fishing hook with a net so vast, so sensitive it can dredge the skies every single night, catching not just one or two but hundreds, perhaps thousands of these cosmic messengers. That net is being woven right now. On a remote mountaintop in the Chilean Andes on Cerro Pachon, A new eye is preparing to open and gaze upon the heavens. It is the Vera C. Rubin Observatory, and it is poised to change everything. It is difficult to overstate the revolutionary leap in capability that Rubin represents. Its primary mirror is a colossal 27 feet across a giant pupil designed to gather the faintest whispers of light from the deepest chasms of space. But its true power lies in its extraordinary camera, the largest digital camera ever constructed. At its heart is a focal plane composed of 189 state-of-the-art sensors chilled to a frigid minus 100 degrees Celsius to eliminate any electronic noise. This behemoth the size of a small car and weighing over 3 tons will capture images of the sky with an unprecedented 3.2 gigapixels of resolution. A single one of these snapshots would require 1,500 high-definition television screens to display at full size. The true genius of the Rubin Observatory, however, is not just its power but its speed. Every 3 nights this observatory will scan the entire visible southern sky. Every 3 nights it will generate a new, exquisitely detailed map of the cosmos. This relentless systematic survey is called the Legacy Survey of Space and Time, or LSST, and it will produce a motion picture of the universe. Over its planned 10-year mission, it will stitch together thousands of these maps, revealing a universe that is not static and serene, but dynamic, violent, and ever-changing. The sheer volume of data it will produce is staggering, almost incomprehensible. Each night it will generate 20 terabytes of information. That is the equivalent of the entire written collection of the Library of Congress produced every single evening. Over its lifetime, the LSST will create a 15-petabyte catalogue of the sky, a treasure trove of cosmic information that will keep astronomers busy for generations. And within that torrent of data, hiding like jewels in a river of sand, will be the interstellar objects. The faint, fast-moving points of light that have until now so easily eluded us. Rubin's immense field of view and its rapid cadence mean that our chances of detection will skyrocket. Instead of finding one interstellar visitor every few years, we could begin to find them every few months, perhaps even every few weeks. They will cease to be ultra-rare curiosities and will become a new observable population of celestial bodies. We will finally have a statistically significant sample size. We will be able to compare and contrast dozens, then hundreds of them. We will see their diversity, their range of colors, their compositions, their trajectories, and their behaviors. This data will allow us to ask questions that were once pure speculation. Where are these objects coming from? Are they being ejected randomly from distant star systems, or do they originate from specific identifiable stellar nurseries? What are they made of? Are they predominantly rocky, icy, or something else? Entirely composed of materials and chemistries born in alien solar systems. Do any of them show the same anomalous, non-gravitational acceleration that made Oumuamua so famous? And most critically, will we ever see another object that behaves like 3I, Atlas? Will we find other visitors trailed by debris that refuses to scatter other formations flying with inexplicable precision? The Vera C. Rubin Observatory will transform these questions from philosophical musings into testable hypotheses. It will allow us to see if 3I, Atlas, was a singular once-in-a-civilization anomaly, or if it was merely the first emissary from a class of objects whose existence we had never before imagined. Furthermore, Rubin's early warning system will be a game-changer. By detecting these objects while they are still far out, long before they reach their closest approach to the Sun, it will give us something we have never had before: time. Time to mobilize other observatories around the world and in space. Time to point the powerful spectroscopic eyes of the James Webb Space Telescope or future instruments at them, to dissect their light and decipher their chemical makeup. Time, perhaps, to even consider the audacious possibility of a rapid response intercept mission, a probe launched to chase down one of these visitors and see it up close to taste its coma and touch its surface. The era of being caught by surprise, of scrambling to observe these objects in the few precious weeks we have, is coming to an end. A new era of proactive, systematic interstellar archaeology is about to begin. This is the enduring legacy of 3I, Atlas. It was more than just a celestial object. It was an awakening. It was the universe tapping us on the shoulder, reminding us that our knowledge is a fragile island in an infinite ocean of mystery. It has prepared us for the coming data deluge from Rubin, priming our minds not to be shocked by the unexpected, but to embrace it, to search for it. We are now looking at the sky with new eyes, armed with a new sense of humility and a boundless sense of wonder. We are no longer just searching for rocks and ice. We are searching for answers to the deepest questions we can ask. What forms can matter take? What physical laws govern the far-flung corners of our galaxy? And the most profound question of all, are we alone? The story of 3i, Atlas, does not end here with its disappearance into the dark. Its story is only just beginning. It is a prologue, a preface to a grander narrative that we are about to uncover. Its passage was a whisper from a distant shore, a promise of the wonders and complexities that await us as we continue to push the boundaries of our vision and our courage. The night sky, once a familiar tapestry of constellations and planets, has been transformed. It is now a hunting ground, a place of infinite potential where any stray photon, any faint streak of light could be the key to unlocking a new reality. The silence of space is not empty. It is filled with the echoes of creation, with the ghosts of other worlds, and with the promise of discovery. We have only to keep looking up, to keep listening, and to be ready for the answers, no matter how strange they may be. For the universe is not only stranger than we imagine, it is stranger than we can imagine, and our journey into that strangeness has just begun.